section is going to introduce tangent lines and velocity. Let's begin with rate of change. Rate of change describes how one quantity changes in relation to another quantity. If x is the independent variable and y is the dependent variable, then we can define rate of change as the change in y over the change in x. You may recall this formula. If we're looking at a linear function, this is the slope of the line. So for example, if we look at f of x equals negative 2x minus 3, we can see for every change in 1 unit of x, the graph is going down 2 units for y. So over 1, down 2. Over 1, down 2. This rate of change is constant for the entire linear function. So if I were to find this rate of change for this line, it's always going to be down 2, the change in y, over the change in x, which is negative 2, which you can see represented here in the formula as the slope. But what happens if we look at a curve? We can see here this rate of change is not constant. It's different based on where we are in the graph. So for example, if we look at the graph from the left, we can see that it starts decreasing pretty rapidly, and then that starts to kind of taper off. It's decreasing still, but it's decreasing a lot slower until we hit this vertex, and then it changes to increasing, and it starts increasing slowly and then increasing a lot quicker. So that rate of change isn't constant. So we quite naturally ask, how do we measure the rate of change of a nonlinear function? Before we delve into that, we need to have some definitions. So let's first recall the slope of a line. The slope of a line between 2 points, x sub 1, y sub 1, and x sub 2, y sub 2, can be defined as follows. The rise over the run, or the change in y over the change in x, so that's what this symbol delta means, is the change. Algebraically, y sub 2 minus y sub 1 over x sub 2 minus x sub 1, or we could rewrite that as the function evaluated at x sub 2 minus the function evaluated at x sub 1 all over x sub 2 minus x sub 1. Now some new terminology, secant. So the word secant actually derives from the Latin word secare, which means to cut. A line that is secant to a curve is a line that cuts the curve. The word tangent. So that also derives from a Latin word tangens, which means touching. So a line that is tangent to a curve is a line that touches the curve at a specific point. We're going to use these two things to help us find the rate of change at a specific value of a nonlinear function. Let's look at the example that we started with when we were defining rate of change, this y equals x squared. So when I have this graph again, you can see that the rate of change is different based on what part of the graph I'm on. On the left-hand side, it's decreasing. On the right-hand side, I'm increasing. And they're decreasing and increasing at different rates based on where I am in the graph. If I wanted to find the rate of change at a specific point on the graph, so let's say I'm trying to find that rate of change right here at this point in purple, which is 1, 1. What we can do one way is we can actually sketch the graph of the tangent line by kind of eyeballing it. So using a straight edge, you can see I've gone through and I've graphed that tangent line in green, in the dashed green. So again, tangent means touching. So this is the line that just touches the curve right at the point 1, 1. And I can use that tangent line to estimate what the rate of change is at that specific x value. So when x equals 1, the rate of change we can see using slope. So it looks like it goes over 1, up 2, over 1, up 2. So we can see that that slope again is that change in y over the change in x, that rate of change. So the change in y is 2, the change in x is 1. So we can estimate that that rate of change is about 2 units. Now this obviously isn't specifically accurate. We're eyeballing it. We're going to get into how to actually find a derivative, which is going to give you that specific rate of change in future sections. So we'd say the rate of change is 2.
Now,
Example, find the equation of a tangent line. Find the equation of the tangent line to f of x equals x cubed minus 1 at x equals 2. You can see here I have created a Desmos applet that's going to help us figure out what the slope is first for that tangent line. So what I have graphed here is f of x equals x cubed minus 1, that's in red. And then I've drawn a secant line that goes through when x equals 2. So when x is 2, the y value is 7 because 2 cubed is 8 minus 1 is 7. So that's what gives us that purple dot. And then I'm going to take and use secant to find what happens as we have a second point that gets closer and closer and closer to that x equals 2 from either direction and see what happens to the slope. So if you look down at the slope formula down here, you can see we've got our a equals 2, which is what we want, a plus h. So what that is this is going to be create our second point. So you can see this a plus h, 1.53 is right here. If I did 2, which is our a, minus 0.47 or plus a negative 0.47 is when we get this. So that h value represents how far away my second point is, this 1.53, from the actual value. So as this h gets smaller and gets closer and closer and closer to that x equals 2, you can see that this value is going down and this secant line is going to start to look more like what the slope of the tangent is there. And again, we're going to use some secant lines to estimate what that slope is so that we can be a little more accurate than just rough sketching a line there. So let's see what happens. In this last table or box that I have here, you can see the slope. So it's the f of this second point, which is that a plus h, or the x value of the second point. So a plus h, 1.9, a plus h, 1.9, minus the function evaluated at the point. So again, that point is when x equals 2. And then you divide that over the second x value, which is this a plus h, minus f of a, which is f of 2. So let's look at what happens. I'm going to put this slider and have it kind of play. And I'll have a link to this applet in the video notes. So if you want to get on here yourself, you can change your own functions, you can play around with it and just kind of visually see what's happening with these secant lines as they're approaching that value. So let's see. So as our h is getting closer, you can see that line is getting closer. And right when we're very close, this slope you can see is approaching, it looks like it's approaching about 12. Okay. Now let's see what happens as I go from the opposite direction. So let's play this here. So again, watch this slope. So as this point, which we can't see right now, but now we can see it, as that's getting closer and closer and closer, this slope is getting closer and closer to 12 as well. So we can estimate that the slope of the tangent line as for the rate of change at x equals 2 on f of x equals x cubed minus 1 is 12. Now we can use that to find the equation of the tangent line at that specific point. Now that I found out that the slope of the tangent line is 12, we can use that in a point to find the equation of the tangent line. So we know that this tangent line is going to touch the curve at x equals 2. So we know it's going to go through the point 2, and then let's figure out what that y value is by inserting 2 for x. I'm going to get 2 cubed minus 1, which ends up giving me 7. So I have a point that's on this tangent line of 2, 7, because it's going to touch the curve at x equals 2, y equals 7, and we have our slope of 12. So since I have a slope and a point, I'm going to use the point slope formula for the equation of a line to find that equation of the tangent. So I get y minus 7 equals 12 times x minus 2. Distribute that 12 through, gives us y minus 7 equals 12x minus 24. And then add the 7 to both sides, and I get 12x minus 17. So the equation of the tangent line to f of x equals x cubed minus 1 at x equals 2 is y equals 12x minus 17. We can also check this by graphing that line on that same applet. So I'll leave that up for you to do. So at this point, you may be wondering, why are we learning about tangent lines? Well, the biggest reason is because of physics. They help us with finding position, velocity, and acceleration of specific objects. So what are those? Given an object's position versus time graph, the slope of a secant line gives us the average velocity of the object, and the slope of a tangent line gives us the instantaneous velocity of the object. Let's look at this in a real-life application. Example, velocity of a runner. The world record for the 100-meter dash is 9.58 seconds and was set by Usain Bolt of Jamaica. His 10-meter splits can be found in the table. Answer the following, converting to miles per hour. Let's start with part A. What is Usain Bolt's average velocity during his run? So velocity is another word for it is speed. So how fast was he running? Well, we know that he ran 100 meters in 9.58 seconds. So we'd be able to say his average velocity is he ran 100 meters in 9.58 seconds. So that's approximately 10.438 meters per second. We can also go through and convert this into miles per hour, and when you do that, it ends up being insane. He was running that at 23.35 miles per hour, which is amazing. Let's look at letter B. Approximate Usain's instantaneous velocity at the 50-meter mark by averaging adjacent secant lines. So to find that instantaneous velocity, what it's asking for is find the slope of the tangent line when at the position of 50. So we're looking at he is right here. So 5.47 seconds in at 50 meters. So to find that, what we're going to do is since this is the information I have, we're going to figure out what's the average velocity as I'm approaching that 50-meter mark. So finding that secant line that goes through those 2 points. And what's the average velocity as I'm leaving that 50-meter mark and moving on to 60. So if we can see what's his speed as he's approaching 50 and what's his speed right when he leaves 50 and average those two together, then it can get a good picture of what his instantaneous velocity is right there. So let's do the first one. Let's look at what happens as he's approaching it. So as he's going from the position of 40 meters up to 50 meters. So if I found that slope of the secant line there, I would be taking the change in y values, which we can see here is 10, and then dividing that by the change in x values, and the change in x values here ends up being 0.83 when you take 5.47 minus 4.64. So if I'm going from the 40 to 50, so as he's approaching that 50 meter, his average velocity there is going to be 50 minus 40 over 5.47 minus 4.64, which gives us 10 over 0.83, and let's use our unit, so 10 meters over 0.83 seconds, which is approximately 12.04 meters per second. And then if I looked at what was happening after he left that 50-meter mark, so what was his speed once he got there and he was leaving it, let's find that average velocity. So that's going to be taking those y values and subtracting them all over those x values. And we're going to get 10 meters over 0.82 seconds, which is about 12.195 meters per second. So now I have that slope as he's approaching it, and I have that value as he's leaving it. So what we'll do is we'll find the average between the two. So when I average between that two, that's what's going to give me that instantaneous velocity. So that instantaneous velocity there is going to be finding the average of those two values. So at 50 meters, so that's going to be taking that 12.04 meters per second plus that 12.195 meters per second and dividing that by 2 because we have two values. So finding the average, you add them together and divide by how many you have. And that's going to give me approximately 12 12.175 meters per second. So if we were approximating his instantaneous velocity at the 50-meter mark, we would say his instantaneous velocity at the 50-meter mark is approximately 12.175 meters per second. Example, projectile velocity. A rock is launched vertically upward from the ground with a speed of 96 feet per second. The position of the rock after t seconds is given by the function s sub t equals negative 16t squared plus 96t. Find the average velocity of the rock over the interval 6, 9. Then find the instantaneous velocity of the projectile at exactly 6 seconds. So let's start with finding what that average velocity of the rock is between 6 seconds and 9 seconds. So to find that average velocity, that's going to be finding the slope of this secant line. So the y value at 9 seconds is taking that function, substituting in 9 for t, minus the y value at 6 seconds, all over 9 minus 6. So the change in y over the change in x. I should probably just do equals. So that's going to end up giving me a value of negative 432 feet minus 0 feet all over 3 seconds, which gives us approximately negative 144 feet per second. So the average velocity of the rock over the interval 6, 9 is negative 144 feet per second. That means that the rock is falling, because it's negative, at a rate of 144 feet per second between 6 seconds and 9 seconds. Now, if we wanted to find exactly what that speed is, that's finding that instantaneous velocity of the projectile at 6 seconds. Again, we don't have those tools yet to have an actual formula that we can plug in and get that exact value, but the tools that we do have, we can find the slope of the secant lines of the values that are getting closer and closer to 6 seconds. So what I'm going to do is let's create kind of a table of values, and if we look at this, I'm going to put the interval, so the time that we're going to look at, and then we'll put that average velocity, and then we can kind of see what's happening. So let's look at values as we are getting closer and closer to 6. So let's first start at from 6 to 6.1. So that difference between those x values is 0.1. So kind of imagine when we were doing those applets earlier, I'm taking that second point and I'm going to move it closer and closer to 6. So we'll look at 1/100th away, 1/1000th away, and we'll see what's happening with that average velocity and see if we can find a pattern. Now, we don't want to just look at what happens as it is leaving 6 seconds. We also want to look at what happens as we're approaching it. So I'm just going to do 5.99, and I'll leave it up to you to do the other ones. So let's figure this out. If I'm looking at the average velocity between time 6 and 6.1 seconds, so what's that velocity there? That's going to, again, be doing that s of 6.1 minus s of 6 all over 6 minus 6.1. So that is going to give us negative 0.976 minus 0 all over 0.1. which is approximately negative 97.6 feet per second. Okay, now let's look at what happens between 6 and 6.01. So s of 6.01 minus s of 6 all over 6.01 minus 6. I'm sorry, this up here should have been 6.1 minus 6. I flip-flopped those around. So again, it's always the change in y over the change in x. So we need to make sure if I'm doing 6.1 first up on top, I need to do the same thing on bottom. So when I go to find this one, I'm going to get about negative 0.9616 all divided by 0.01, which is about negative 96.16 feet per second. So we can see it looks like it's starting to kind of get closer to 96, but let's keep on going just to make sure. All right, so let's look at what happens as I get closer. So I'm only I'm 1/1000th away from that exact value I'm wanting to look at. So this secant line is going to be getting so much closer to looking like a tangent line now. All right, so when I do that, I'm going to get negative 0.096 all over 0.01001, which is about negative 96.016 feet per second. And then if we go through and do the same thing for 5.99, so now we're approaching this value from values that are lower than it. I'm going to let you kind of do that one by yourself, but you'll end up getting negative 95.984 feet per second. So what do you notice here? This actually should be. So what I notice when I look at this is I see that as I'm approaching 6 from numbers that are larger than it and numbers that are smaller than it, it looks like we're approaching about negative 96 feet per second. So I can say that that instantaneous velocity at 6 seconds is about negative 96 feet per second.